Hello, I'm Diary, a master's course of GTM Lab. The paper I'm going to review today is a data-driven approach to establishing a patent strategy by generating a patent map based on generative topographic mapping. First, the bibliographic information of the paper. The paper was published in the journal TFSC in 2025, and the keywords and highlights of the paper are as follows. The table of content for the presentation is as follows. First, I will introduce research background and purpose. As economists shift toward knowledge-based competition, patents have become strategic assets for protecting and extending technological advantage um, amid intensifying liability and litigation. Yet, patent disclosure heightens competitive pressure, underscoring the need to read competitors' positions and identify technology vacuums that signal untapped opportunities. Prior studies split into qualitative approaches and quantitative analysis that rely on keyword or IPC codes, often missing form level positioning and nuanced competitive dynamics. A method that captures functional technical content, visualizes the broader technology landscape, and links results to corporate strategy is therefore necessary. So, this study integrates qualitative insight with quantitative analysis by extracting subject action object relations from patent text and applying generative topography mapping to build patent maps. The approach aims to visualize firms' technical positions, reveal competitive patents, and surface actionable patent strategy options grounded in objective evidence. And it addresses the three research questions. This chapter is the background of the study. First, patent strategy plans applications and development using technology trends and friendly data. It also uses patent information to identify competitors and target technology fields. The technology space view focuses on innovation cores and positions that shift with library. Core tactics are blanking, fencing and surrounding, deployed as portfolios rather than single patents. Prior work is abstract or bibliographic, so this study instead visualizes technology positioning with patent maps to make strategy actionable. Next, this page provides background on the models used in the method. GTM is a probabilistic nonlinear dimensionality reduction method and a Bayesian counterpart to SOM. It maps patent onto a 2D or 3D latent grid to build a patent map. An inverse mapping places data on nodes, revealing vacuum nodes and their technical meaning. Prior work used GTM to make roadmaps and find technology vacuums but relied on keywords. So this study adds technical feature information and a form view to visualize strategy and locate competitive vacuum areas. SAO addresses image or keyword methods that rely on frequency and co-occurrence. SAO decomposes text into subject, action on, and object triplets. SAO encodes explicit functional meaning and an invention's core concept. Prior studies used SAO to find opportunities and build technological trees. However, they seldom reflect firm level positioning or patent strategy perspectives. Let me explain the research concept and overall framework. This study built a GTM-based patent map from SEO-derived technical features to validate cross-form positioning and extract patent strategy patterns. The overall research process is as follows and consists of two modules. I will explain each step in more detail. Module 1-1 gathers patent defines the field and selects target and library forms. The collection and pre-processing process is as follows. Module 1-2 extract SAO tuples from title, abstract, and claims using a parser. Complete SAO sentences are tip-by-tip weighted to identify core functional statements. Core SAOs are finalized to build a weighted pattern SAO matrix capturing technical features. Module 1-3 feeds these metrics to GTM with grid size K and RBF parameters M and S plus regularization. GTM forms probabilistic technology nodes, responsibility give membership, and inverse mapping profiles vacuum nodes SAO distributions. Module 1-4 cluster GTM coordinate via k-means to define independent sub-technical areas for strategic use. Module 2-1 profiles technology nodes using the GTM map. Nodes are typed as target, competitor, or mixed. Focus is placed on target nodes to evaluate strategic connections. Image control detection traces boundaries of contiguous, same-type areas on the map. This yields an interview view of form-centric clusters and their linking structure. In Module 2-2, this study translates node connections into strategic intent. Orthogonal links mean blocking, while diagonal links mean expansion. This yields two types, defensive expansion and aggressive blocking. Defensive expansion connects A nodes to A or vacuum nodes diagonally to secure space and keep options open. Aggressive blocking links 3 or more A nodes orthogonally to build a patent wall that blocks B or C growth. The expanded or block examples on the slide show how these patterns are formed. The study derives three patterns from target node connections and contours: blanket, fencing, and surrounding. Blanketing links A node with vacuum nodes to create a broad minefield of coverage. Fencing combines A nodes and vacuum nodes to build patent walls that block libraries development passes. Surrounding encloses a competitor or mixed node with A nodes to fully block use and expansion. Extraction is rule-based. Blanketing uses defensive diagonal links and vacuum occupancy. Fencing uses aggressive orthogonal links plus vacuum-induced walls. Surrounding locates B or C and applies aggressive links with vacuum node to close the loop. This study enumerates all feasible patterns per node to surface actionable options. In Module 2-3, this study applies a GTC classifier to each vacuum node to predict the most likely occupying from and its probability using GTM responsibility and form labels. This probability acts as a forward-looking urgency signal. In Module 2-4, this study score and rank or candidate strategic patterns with three indicators: urgency, superiority, and ripple effect. All indicators are normalized and equally weighted to compute a composite score. Patterns are then ranked by the study score to set clear, data-driven strategic priorities. Next chapter is illustrations. Autonomous vehicles are selected as the illustrative domain. They are dominant due to advances in ADAS and strong AI-driven investor interest. Because the field spans many topics, stakeholders need to in-depth analysis of areas, hotspots, libraries, and partners. This study collected 27,107 USPTO patents from 2010 through 2021 and cleaned both text and metadata. For a one-to-one library, Toyota is the target with 1,336 patents and LG the competitor with 1,238. This study extracted SAO from their patents and built a patent SAO matrix for training and testing. Using GTM, a two-dimensional GTM on a 40 by 40 grid produced 1,600 nodes, and the study clustered the coordinates into four subtechnical groups labeled by CPC. Interactive video and ADAS control, data placement and wireless management, autopilot and control, and navigation-centric ADAS. Clusters 2 and 3 share multiple CPC codes, indicating similar technical configurations. The figure and table below describe the patent map creation process. Here, this study time nodes by firm and visualize their positions. Toyota only nodes are labeled A and colored blue. LG only nodes are labeled B and colored red. And mixed nodes are labeled C and colored green. Overall, Toyota holds 17 more technology nodes than LG, indicating a stronger position. Occupancy is largely exclusive when counted by firm. In cluster 0, LG has 11 more nodes, roughly 5%, so the rivalry is close. In cluster 1, LG dominates with 150 more nodes, about 51%. In cluster 2, Toyota leads with 53 more nodes, about 25%. In cluster 3, Toyota strongly leads with 125 more nodes, about 57%. Image control analysis highlights connected Toyota A nodes in cluster 0, 2, and 3 as the most stable zones for strategic formation. In this map, the Toyota A node contours yield three strategic patterns: blanketing, fencing, and surrounding. In cluster 0 and 1, blanketing dominates, signaling diagonal defensive expansion where liability imbalanced or tilt toward LG. In clusters 2 and 3, fencing dominates, indicating orthogonal aggressive blocking where Toyota's position is much stronger. Overall, the prevailing pattern follows local liability, using defensive blanketing in parity or LG leaning areas and deploying aggressive fencing where Toyota leads. This study trains a GTC classifier on GTM responsibility and form labels to predict the occupier and probability for each of the 637 vacuum nodes and maps through research to 110 candidate strategic patterns. Priority scoring shows that most high priority patterns occur in cluster 0 and 3. The top result is patent 45, a surrounding strategy in cluster 0 that fully blocks an LG node where LG is slightly dominant. The second is pattern 101, a blanketing strategy in Toyota dominant cluster 3 that links Toyota A nodes with vacuum nodes to preempt risk. The 3 and 4th are patterns 36 and 30 with score with 30 Fencing strategy in cluster 3 that builds patent wars against LG expansion. This study then elaborates and verifies these four highest priority patents as exemplary for future strategy. This study validates for high priority patterns 45 surrounding, 101 blanketing, 36 fencing, and 30 fencing by mapping test period patents from 2020 to 2021 onto the GTM map trained on 2010 to 2019 and checking which from developed the target nodes. For patents for 5 and 101, no new vacuum nodes appeared, indicating no additional development beyond existing Toyota A nodes. For patent 36, one new vacuum node 792 and 5 additional technology nodes emerged. For patent 30, two new vacuum nodes, 189 and 268, and 9 additional technology nodes emerged, or newly developed nodes belonged to Toyota rather than RG, consist with Toyota's stronger position in those sub-areas. This result suggests that fencing patterns and metallurgy alleged in practice, while surrounding and blanketing opportunities remain open, likely due to fast-moving advances in autonomous vehicles. Using inverse mapping of SAO content in the relevant vacuum nodes, this study then outlines concrete next-step strategies for each pattern. This study proposes a quantitative patent strategy framework that overcomes limits of expert-driven bibliographic approaches. It models technical function through SAO and visualizes the landscape with GTM, enabling pattern discovery and measurable indicators, thereby advancing theory by linking functional text mining to patent map analytics. In practice, this study helps assess competitive position, drive blanketing, fencing, and surrounding patterns, and exploit vacuum areas. GTC predicts likely occupiers of those vacuums to signal urgency and timing. GTM views translate complex structures into clear guidance for non-experts. Overall, this study aligns with data-driven technology management by turning patent data into actionable strategy. This study proposes an SEO-driven, GTM-based framework that maps the technology space, classifies nodes as target, competitor, or mixed, and drives blanketing, fencing, and surrounding patterns. Patterns are priorities using a GTC predict occupancy vacuum node together with node level indicators, and the approach is validated on autonomous vehicle data where high priority patterns align with later Toyota developments. Theoretically, this study embodies functional SAO information into GTM and advances patent map analytics beyond keyword counting. Practically, it provides intuitive visuals, reduces expert bias, and accelerates R&D prioritization. Economically, it directs investment toward high leverage vacuum areas. Limits include the one-to-one rivalry framing, a short validation horizon, the absence of economic, social, ethical, and legal factors, and narrow strategy set. Future work should model one-to-many competition, test additional industries, incorporate non-technical factors, and extend strategies to include licensing and collaboration. This is the end of the presentation. Thank you for listening.